This lecture video continues the theme from last time, the design of the IoT devices. Specifically, we look at the process of prototyping. So what's prototyping in the first place, and what's the minimum required to design and build IoT devices? Let's start by recapitulating a little from last time. So here are a couple of terms. First, ubiquitous computing. So ubiquitous computing is computing that is made to appear anytime and everywhere on any device, any location, or in any format. So our users or people interact with computers that exist in many different forms. Those include laptops, tablets, and terminals, and also everyday objects like fridges or eyeglasses. Then we had the idea of designing for ambient technology. So ambient technology meant the consideration of all contexts in the design. So objects are not designed in isolation of the surrounding world, but in fact just the opposite. Ambient technology considers how the device interacts with its surroundings. Palm technology is the term used for systems that blend into their surroundings seamlessly. The normalcy field is the perimeter which the devices have to cross to be adopted by the general public. Affordances provide strong clues to the operations of things. So, for example, plates are for pushing and knobs are for turning. Privacy is a never-ending quest in the design of the IoT. Even the most seemingly innocuous applications can collect personal information, and in the worst case, they can leak data. Both designers and users should be alert to this danger and take measures to avoid it. Then let's start to think of the topic of prototyping. So what is prototyping? We know prototyping by intuition because most lab work in school is about prototyping. We are not preparing ready solutions to be sold in shops for big audiences in the market, but rather we are making prototypes. Prototyping is the process of creating working models of products or systems. When it comes to IoT systems, making prototypes, it's required to have some design skills, some electrical skills, some physical and mechanical skills, programming knowledge, and also to understand how the internet and TCP/IP and other various networking protocols work. Besides these skills, because the IoT is still a developing field, there is some knowledge that could be useful when prototyping for IoT devices, but it's hard to pinpoint them because of this immaturity of the field. All we know right now is a great time to invent something that is part of the IoT because the field is really growing. To recap, a prototype is something of the following. First, fully functional version of a product, but in no means fault-proof. It is an actual working version of some system or product. Usually prototypes are used for performance evaluation and further improvement of the product. Prototypes have a complete interior and exterior looks, and they are inexpensive to produce. And in IoT and in technology fields in general, they are often used as a technology demonstration. Why should we prototype, or why should we build prototypes? Why not just build straight into production? Why not build ready products in the first place? Well, prototyping is a tool that lets you demonstrate an idea with the least amount of work. So a prototype does not have to be a finished product. All it has to do is convey the idea of this smart system that you want to build. Arguably, designing new systems is hard, and the problem with presenting plans for new systems, well, there are multiple problems actually. First of all, plans usually are incomplete, they can be very naive, plans can turn out to be infeasible, and it's really hard to know if something is doable or not. It is really hard to answer the question, how do we know that we can build something? Most importantly, plans usually do not tell anything about this product's or prototype's realization, as in how is this thing actually constructed. We don't know key details, for example, how should this thing exactly work, who is going to build it, how is that person going to build it, and what is the guarantee that following a plan results in what we promised in the plan or what we started out to plan. Prototyping as a process tries to alleviate some of those problems. So we build prototypes with the least amount of work because then we can distinguish good ideas from bad ideas. The following couple of pages in this lecture slides contain examples of good and bad design, and the idea here is to demonstrate why prototyping matters. And it's easy to see these good design ideas versus the bad design ideas by using concrete examples. As a disclaimer though, I am not a designer in any way. So these are just examples that I have run into on the internet. They are not my own designs, and I am not qualified to actually rate, even talk about good design in any way. But all in all, I just want to get the main ideas across here. So this is just a disclaimer. Let's take two practical examples of something that was not very well designed. So take a look at this street sign here, which basically tells you information about when parking is allowed and when it's not allowed. Let's just take or pause the video right now just to think of what this sign actually wants to convey. So as said, the prototyping helps distinguishing good ideas from the bad. And arguably, the design of this street sign is not very good. For one, you're probably driving when you look at street signs. So trying to absorb all of the information that this sign wants to convey is never going to be possible. So secondly, some of this street sign is so full of information that probably some of these parts can be temporarily blocked by people who are passing by or a bigger car that's parked in front of it. So it suffers from all sorts of problems when it comes to design. Okay, so while the street sign is not exactly an IoT device, the point that I want to come across is that things that we encounter every day in our homes, on the street, in our jobs, at school, they have to be intuitive. And in that street sign, there was a lot of information overload. I'm sure all of that information is necessary, but could it be conveyed in a better sense? So let's take a step back and think, how do you tell something is good design? Well, design is more art than science, but there are some heuristics, some rules of thumb, if you like. One of these heuristics is don't tell a user what they can't do, but do the opposite. Tell what they can do. So in that street sign, there were a lot of restrictions as to when parking is not allowed, but that's probably not the information that these drivers want to know. They simply want to know whether they can park. So they want to know when it is allowed to park, not the opposite, which was what the street sign wanted to convey. And also, you don't need such an information overload. All you need to know is yes or no. We will probably in the future have some smart street signs that will be able to convey such information in a much more neat way, but for now we could design something better. So for example, this suggestion on the right here is an improvement of the original idea. So here the idea was that we want to understand what the users need and then design based on those needs. So for example, if we have a lot of information that we need to convey, so let's not print it out, let's not use text, but let's use some visuals instead. Okay, another example. What about this very pretty animation that is printed out from a web shop when you have made a purchase? So this is all very pretty, so arguably the design is very nice, but the animation is very superfluous, meaning it doesn't actually do anything. All it does, it will take the user 3.5 seconds longer to see all of those transaction details. So rather than being useful or pretty, it ends up being annoying. Okay, let's return from this very shallow dip into the world of design and go back to the topic of designing the IoT. So basically all students here at this point will have most of the necessary skills to create IoT devices or smart systems, because you know programming, you know the networking fundamentals, you know electronics, you know physics. So what more is missing? Why isn't everyone building great IoT devices? Well, on paper, there is nothing missing. So far, we've even created prototypes of smart things or IoT devices in the labs. The only thing here is that they are still prototypes. They are not ready to go to production. They will not employ someone full time. So at this point, we have to recognize the limits of what prototyping can do. So at the end of this stage, you will have something that works. It may be useful for you already. It may be a good talking point to show to your friends. And if it's a really good idea, you might be able to demonstrate it so you can use it to convince yourself and some business partners or investors that this idea is really good and it's actually worth trying to redevelop and eventually sell. Prototypes are very far away from mass production or industry. You might need to substitute some of the prototyping tools, microcontrollers or single board computers and wires with smaller chips or printed circuit boards. You might have designed some pieces of the smart thing with less than flexible and durable materials like cardboard or 3D printed custom plastic components. Those would be replaced with injection molded mass-produced plastics. If you were to manufacture your prototype, the final product would probably be cheaper to manufacture and look more professional, but it would be at the end very much more expensive to change. So beyond the prototyping process, when moving from prototypes to production, it's worth to consider the costs that arise from the actual mass production of devices. This is a trade-off that's not really hard and fast, but it's beneficial if you can choose a prototyping platform in a performance or capability bracket that is similar to the final production solution. Now, maybe we need to consider a little what type of tools, microcontrollers, electronics we can use to prototype and what kind of devices can we use in mass production. So the cheapest possible way of creating an electronic device is currently something like an AVR microcontroller chip which you can buy from a component supplier for about €3. This price is just for the chip, so you would have to connect those pins on the chip to other components. You would have to flash the chip with new code, and again, this component on its own has no connectors, no power source, no memory as of now, so all of those would add to the cost. And that additional cost and complexity is actually the reason why we don't prototype on pure microcontroller chips. What we use are microcontroller platforms. So if we step upwards to the 10 to 30 euro mark, we could look at Arduino boards or similar. In the labs, we use the ESP32, which costs around 15 euros to buy. They have more or less the same chip inside, but they are laid out on a board with labeled headers that help you to wire up the components more easily. There is also a USB port where you can plug it into a computer, and the computer and software will do the flashing of the code for you. There is usually also a pretty well supported integrated development environment to make programming easier. Of course, we are still programming in C or C++, which are very low-level programming languages for reasons of performance and memory. If you don't want to consider performance and memory restrictions, you could, for some more money again, look at more expensive platforms. So you could look at something like the BeagleBone or the Raspberry Pi. These are single-board computers that run Linux, and they have enough power and RAM to be able to run a high-level programming language and an operating system. So now you could use libraries and programming languages provided by software libraries like Node.js or JavaScript and use high-level programming languages. Or why not Python or C? All of those languages and environments are well supported. In addition, if you really don't need the I/O pins or you want to move computation away from the hardware, you can also consider running some of the code on your PC or tablet or phone. Once again, going a bit beyond prototyping, what would it take to make a production version of your prototype? So scaling up to build more than one device, perhaps many thousands of devices, that brings a whole new set of challenges and questions. So, for example, what if after design you have to change the embedded platform? So when you scale up, you may well have to think about moving to a different platform for cost or size reasons. If you've started with a free-form, powerful programming platform like one of those more expensive platforms, BeagleBone or Raspberry Pi, you may find that porting the code to a more restricted, cheaper, smaller device will bring many challenges. So for example, the Arduino devices have a dynamic memory allocation of 2 kilobytes, and that may not be especially efficient. So how would you make use of that if you think about something complex like strings of text or complex data structures? If you port your code to a more powerful platform, you may be able to rewrite the code in a more modern, high-level way, or simply take advantage of faster processor speeds and more RAM. So if you do the opposite, you expect not to have very much troubles, but will that new platform have the same I/O capabilities? And you do have to consider that the ramping up time to learn the new technologies and languages will also take some of your mental capital.